on my guest, Chris Schweitzer. And I hope I'm saying your name right, Chris.
That's close enough. It's actually Schweitzer.
Okay, Schweitzer. Sorry about that. How are you tonight?
I'm great. It's really a pleasure to be on late night in the Midlands.
Well, it's just as much a pleasure to have you here tonight. So I have a feeling I'll be learning something.
I hope so.
All right. So I guess why don't we start out? Tell me a little bit about yourself and then a little bit about this book.
Well, I'm a paranormal researcher,
Mm-hmm.
and I'm also a quantum physics researcher. And when you put those two together, you come up with some things that are awful close together. They call me the reality is paranormal guy.
Right.
What I do is I show the skeptics and the critics who dismiss paranormal experiences that the physical world is just as bizarre and just as inexplicable as that which is found in the realm of paranormal.
Okay. So what do you mean by that?
Well, I challenge the critics and skeptics of paranormal experiences with examples of how nature acts in bewildering and mysterious ways that no one can explain. I do that by explaining the simple fact that everything, all forms of matter, what you and I, all of us are made out of, or composed of, in fact, our whole universe, that the very laws of nature are by definition paranormal. So what is the definition of paranormal? It's something that is impossible to explain scientifically, or something that cannot be understood in terms of scientific knowledge.
Mm-hmm.
Now, with the numerous unexplained paradoxes found in quantum physics and cosmology, they fall under that definition. Nature does things that, by all intents and purposes, are impossible to understand by our understanding. I can give you some examples.
Yes, please do.
In quantum physics, there's something called the wave function collapse. It's also called the observer effect. And it's a demonstration of the duality that is the dual state of matter. All matter on the subatomic particle level exists as both a particle and a wave. I'll get into that later, but right now we're just get a little groundwork going here.
Yeah, a little understanding.
Right. So, like I said, it's scientifically proven fact that all atomic matter exists as both a wave and a particle. To visualize what I'm describing, you have to eliminate that picture we were all taught in school where we were told that an atom is a nucleus with electrons orbiting around it like planets orbiting the sun.
Mm-hmm.
But the truth is that electrons are, in actuality, they're a wave just like in a pond. It's actually a wave of energy. It's not a particle. And like all waves, the electron wave has a crest and a trough. Just like when you're surfing a wave, you're up on the crest and you surf down into the trough. Now the energy of the wave, the energy that is in the electron dictates the height of that wave or the crest of the wave as it races around the nucleus. So if you can imagine a wave with a peak and a trough, and that's what's moving around the nucleus. It's not a solid particle.
Okay.
Now, it was discovered over 100 years ago, what I'm talking about now. This is nothing new. It's not something I made up, and that's the way nature is. And it can be demonstrated, and before we're through tonight, I'll let your listeners see for themselves what I'm talking about with just their bare hands. Kind of a parlor trick I like to show.
Okay, that's fine. Now, tell me about paradoxes and quantum physics and what they actually have to do with the paranormal.
Okay, well, like I was saying about the fact that matter is a wave and it's a particle. Now, matter is in this wave state that I'm talking about when it's undisturbed. It's a wave of energy, and it typically stays that way until it interacts with another wave. when a wave interacts with another wave of greater or lesser energy, it collapses that wave, and that wave becomes an actual solid particle. And that's what is called the wave function collapse.
Now, what about like dark matter? What is all that now? Is that different from what we're talking about, or?
Yeah, that's something different.
Oh, okay.
What I'm talking about right now is just the basic material that makes matter. That is everything that is solid in our universe.
Okay.
But everything in our universe is not solid. It's every little subatomic particle and all the things that atoms are made out of, neutrons and protons. They are not solid particles until they interact. They're waves until they interact with another wave. Now here comes the paranormal part.
Okay.
Now, stay with me for a second. I know it's confusing.
I'm doing my best.
Okay, this wave function collapse is also called the observer effect. It only sounds complicated. But the wave also collapses and turns into a particle, like I was saying, when we observe the wave. I'll repeat that. The wave turns into a particle when we observe the wave. In other words, the wave functions, that is, it behaves like a wave until it is either observed or a measurement is taken. Then the wave collapses and it functions or behaves as a particle. How is that possible? No one, not Albert Einstein, Stephen Hawking, or any other physicist, knows how or why the simple act of observation can affect the nature of reality.
Has this been documented?
Oh, absolutely. Like I said, it's over 100 years old. Mm-hmm. And I'll show you how you can see it yourself with your own bare hands in a moment.
Okay.
Now, there's a lot of theories, but none has ever shown any promise of explaining wave function collapse by observation. Wave function collapse is more than paranormal. It's supernatural. It's beyond explanation. Now, how is it that if you look at something, it changes? You don't touch it. All you do is observe it. Now, there's something called the slit screen or the double split or the double slit experiment. Now, in the double slit experiment, like I said, it's been seen more than 100 years ago. In a physics lab, a barrier is set up with two closely spaced parallel slits cut in it. Each slit can be opened or closed independently. Now, you can do this with a razor blade and a piece of cardboard.
Mm-hmm.
You don't have to go into a laboratory, just a thin piece of card, a playing card. They put two razor slits real close together, side by side, half-inch long or so, and in a darkened room, put a flashlight in front of those two slits on the card and shine it onto the floor or onto your desktop. And what you'll see is not two slits of light. You'll see a series of bands.
Right. Mm-hmm.
And these bands, there can be any number of them. In fact, they can, at times, under laboratory conditions, number infinitely. But, again, in the lab, you put up this barrier with the two slits. Now, each one of these slits can be opened or closed independently. Now, that barrier is placed in front of a screen like a movie theater screen.
Right.
Now, with an apparatus much like a movie projector, you can project a stream of subatomic particles, electrons, atoms, or photons towards the slits. The intensity of the stream of the particles is set to a point where only one particle passes through the slit at any one time. Thus, each particle can encounter the slit which it passes through, and it registers on the screen. Or the particle can hit the barrier and is absorbed. Now, even if the stream is perfectly aimed, no one can predict just where an individual particle will land. But every time a particle manages to pass through the slits in the barrier, it leaves a tiny spot on the screen. So you would think each particle must pass through one or the other slit in order to reach the screen.
Mm-hmm.
They don't.
What do they do then?
They interfere with themselves. And that creates this pattern, the pattern of the series of separated bands, the sequence of stripes I was just telling you about. Now, if you close one slit, you'd expect to see one band, one strip, corresponding to the shape of your slit. But that's not what you see. You see the screen with one slit open. It's covered with random hits, scattered all across the screen. Again, the question is, why and how can a particle interfere with itself? Now, I'll have more to talk about that later, but that's exactly what it's doing. See, a particle cannot interfere with itself. If
All right, well, listen, we have to take a break, and when we come back, I want you to finish that, and then I want to get into what this all means. I mean, as to just having this knowledge, where can this take us? But just hang on a minute. I'm Michael Vera. This is Late Night in the Midlands. We'll be back in just a few moments.
all the stuff that there is, everything that we see, everything that our universe is made out of, that's the reality. But
right.
In fact, our reality is paranormal. And science tells us that. Quantum physics tells us that. I was talking about the double slit experiment,
mm-hmm.
where a particle, it makes a choice. One particle now, it's either going to go through one slit or the other slit. It has two opportunities to make a fact, to show us reality.
Right. I'm following you now.
Okay.
I really am.
But in some way, the opportunities, the two possibilities, somehow affect one another. They interfere with each other.
So does this tell us where we come from or what we're about? I mean, is this kind of lead us to that?
The science leads us to that.
Mm-hmm.
And that, in turn, leads us to what could be the answers for so much paranormal experiences.
Okay. If you don't mind, I just want to cut you off for a second. We've had a caller waiting on the line since we started here, so I'm going to go ahead and bring him on. He has a question. Donovan from Ohio, you are on Late Night in the Midlands, Donovan.
Hello, Michael. How are you?
Doing fine. Yourself?
Good. My name is Donovan Denholm. I'm from the Project T website at paranormalexperiences.net.
Mm-hmm.
Chris posts a lot of his blogs on my website.
Oh, okay, great.
Like you said, they're fascinating, but I consider myself to be a pretty smart guy, and he makes my brain hurt. I did have a question for him. I'm hoping to stump him. I'd like to know what his theory about shadow people and black orbs are, and I'll go ahead and take my response off the air so I can listen.
All right, thank you.
Thank you very much.
Okay, thanks for calling. All right, Chris?
Yeah, I know who Donovan Denholm is. He's got a great website, the paranormalexperiences.net. Got like 1,200 people who come in and log on their experiences, and they talk about what goes on. It's got psychics and tarot card readers and out-of-body experiencers, UFO abductees, ghost hunters.
That's some great stuff right there. I mean, you know, I have, speaking of tarot card readers, I have one. I don't want to get you off the question here, but there's one, her name's Heather Woodward, and she's been on the show a few times, and I'll tell you, some of them are amazing. Yeah,
there is amazing things. The slit double screen is amazing. What did Donovan ask?
He wanted to know about shadow people. Your opinion on, right?
Yeah.
Shadow people, yeah. And orbs, I think it was.
Well, a little later in our little science class here, we're going to talk about parallel universes.
Okay.
Parallel universes are not science fiction. They're science fact. And if Donovan wouldn't have called, I would have gone on to explain that one of the answers to the double slit phenomena of how a particle can leave an apparatus as a particle, go up to a screen that has two slits in it and change from being a particle to a wave, go through both slits, then interfere with itself on the other side, and then travel through space and hit the screen in the back as a particle is paranormal. But that's how all matter is. It's dual existence, both particle and wave. Now, one of the answers is, well, that is two particles going through. One is a particle from this universe, our universe, and the other particle is from a parallel universe. And those interfere with each other, and they combine together and hit the screen.
Mm-hmm.
Now, when you're making the, let's say, photons, we can be using electrons or any other particles, but photons, a little particle of light, and it passes through, it leaves your apparatus projecting a light, single photon. It goes up to that screen and decides, well, I'm not going to go through the slit on the left. I'm not going to go through the slit on the right. I'm going to go through both of them. So I'm going to change from being a particle to being a wave.
So there's some intelligence behind it?
Well, a religious person would say God is behind it.
Okay.
Other people would say, well, no, it's just a matter of evolution and the evolving of all these multiple universes to where you mentioned it earlier in my intro about the anthropic principle of human making, and that is that our universe is one of the parallel universes where everything is just right. It's what they call fine-tuned, and we'll get into that when we talk about the fundamental constants. But yeah, I do have an idea about what shadow people and dark orbs are.
Good. Tell me, because I am absolutely interested in that myself. That was a great question, by the way.
Yeah, it is. Now, I'll use the double slit experiment to demonstrate that. Like I said, when the particle turns into a wave, it passes through the slits and interferes with itself. Well, everywhere that a crest of the wave meets a crest of a wave, of the other wave, they cancel each other out. Now, here's what your listeners can do, and you can do there and your staff. Make an OK sign with your hand, your finger, your first finger and your thumb.
Okay.
Like, okay, buddy.
I'm doing it now.
Okay, now in front of a light source like the monitor of a computer screen or a light bulb, don't ever do it in front of the sun. but in front of any light source. Now, as tiny bit as you can, separate your thumb, put it in front of your eye, or eyes, and pull your thumb and your finger apart just the smallest amount that you can barely do, like the thickness of a strand of human hair.
Yeah, and you can see like almost some energy there.
You see a black line or a black dot.
Yeah, it's almost like accordion, kind of.
Oh, okay. Now, some people, their fingers shake too much, or I've been able to do it by taking two playing cards and holding them up in front of a light and just bringing them within a hair's distance apart.
Yeah, I see what you're talking about now, yeah. So,
okay, well, what's happening is the light that's coming towards your eye is trying to squeeze between your fingers, your finger and your thumb. And the crest of this wave that I'm talking about is interfering with the other crest of the wave, and it's canceling it out. So what you're looking at, that black is the pure blackness that black can be. There's absolutely no light there. It's canceled out.
Uh-huh.
Now, again, I'm being forced to jump ahead of myself here.
It happens to me all the time.
But if we are to go along with Stephen Hawking, and I can list Alan Guth, Lisa Randall, all top theoretical physicists from around the world. A recent survey of 72 of the top physicists, I think it was 58%, said absolutely positively there are parallel universes.
I believe so, too.
Good, because there are. And you can send them to me if they want to argue about it. But what would a shadow person be? What would manifest that? What's the mechanism that would create a dark black figure or a dark black orb? Well, it's the same thing as what we're doing with our fingers here. But instead of being a thumb and a finger, it's two parallel universes.
Now that makes sense.
That are well, according to the head honchos in the science department, these other parallel universes are a thousandth of a thousandth millimeter apart, which ain't much.
Mm-hmm.
So if you've got an opening, a space between two parallel universes, then any energy trying to come between is going to interfere with itself. Because a parallel universe, the laws of nature are the same. Otherwise it wouldn't be parallel. So one theory, my theory, is that what's happening when a person is observing a black orb or a dark, lightless shape is that they're seeing between two parallel universes.
That's actually the first time I've heard that theory, and I like it.
Well, that's in my book, and when it's published, you can read all about it. Again, I think you said the book really isn't for the average reader. It's a lot of heavy science stuff, and I really wrote it for some of these ideas that I have about the actual nature of reality.
Okay, hey, if you don't mind, let's take us another call. We have Tony from Arizona on the line. Tony, you're on Late Night in the Midlands, my friend.
Hey, Mike.
Hello.
How you doing? How you doing tonight?
Oh, I'm doing great. And yourself?
Good. Yeah, well, not great because my internet ain't working right. So I was kind of like bleeding off somebody else's line, but now I lost it completely. But anyway, it sounds like you have a pretty intelligent guest tonight, and I was just wondering on Glenn Beck's show tonight, they had this child prodigy. He was like 12 years old, and he was talking. He actually he's debunking Einstein's theory of relativity, and that he says he actually has two other. He discredits the Big Bang theory, but he says he has like two other. I mean, this is out of a 12-year-old kid. I thought it was pretty interesting.
I've seen some of that tonight, Tony. Yeah, so I know what you're talking about. But go ahead.
Yeah, I was just wondering what he thinks of that. I mean, they said the guy's IQ was like 170 or something like that, and he said he definitely discredits the Big Bang theory, and I guess he's probably going to have him on at a future date. But I was just wondering what he thought. What's his thoughts on the Big Bang theory?
Chris?
You want my thought on the Big Bang theory? Well, I agree with the young prodigy. There was no Big Bang.
All right.
Now, in quantum physics, well, actually cosmology is the science, says that the universe came from what's called a singularity. When you look up a singularity, well, that's something that has no dimension and no size.
Okay.
So how can something that has dimension and no size, something with no dimension, no size whatsoever, no mass, doesn't exist. So you immediately say, well, what you just said, that the singularity of the Big Bang, the definition of a singularity is something that does not exist. But beyond that, I don't want to go into singularities because that'll take us into black holes. But no, let's get back to parallel universes. That's right now really the top dogs. pretty much agree that the Big Bang was not a Big Bang, it was a big bump.
A big bump?
Yes. It was a...
Okay. Never heard it described like that, but okay.
Okay, well, I was talking about parallel universes. There's all kinds of different universes. There's also multiple universes. Now, in string theory, you've got 11 dimensions, and the 11th dimension is a place where these other universes, that's where they're...
Now, how do you measure a dimension?
Well, our dimensions are up, down, right, left, forward, backward, up and down, and time.
Oh, okay.
So they're what called, they're spatial vectors.
Mm-hmm.
A dimension is how you describe a space. Now, again, string theory, there's 11, because we have up, down, right, left, forward, backwards, and time. But in string theory, for string theory to work, you've got to have around and around. You got to have inside out. You got to have donut. You got to have open donut and closed donut. And we can go on, and we'll get to 10 of those dimensions that are required for string theory to be real. And string theory saying that these particles that I'm talking about aren't particles; they're actually little vibrating strings of energy, which in a way they are. That's what a wave is. It's a vibrating string of energy. But in this 11th dimension, Michio Kaku, if you've ever seen him, a fellow who does a lot of science stuff on television shows trying to explain time travel and black holes, and he's always called in on CNN as a science expert. He has a book called Parallel Universes, and he describes it as the 11th dimension is like, our universe is like a bubble floating in a sea of bubbles.
Uh-huh.
Now, when I say the big bump as opposed to the big bang, the big bump was where two of these bubbles bumped into each other in the 11th dimension. And when two bubbles bang into each other, the energy of those two combine to form a new universe.
One big bubble.
Well, no, it creates another bubble. So, well, yeah, anything's possible. So one could say, a small bubble could join up to another baby bubble and become a big baby bubble. But in our case, it is pretty much agreed that two universes banged into each other, and that's where the Big Bang came from. So I agree with the 12-year-old prodigy that there was not a singularity, like we have been told, but it was two universes that banged into each other, and that's what created our universe.
Yeah, because I was kind of curious how you get something from nothing.
Right.
Like that, so...
Now, the only problem with this is, where did those two universes come from?
There you go. Serious question never ends.
Yeah.
It's like the thing, well, what is the Earth sitting on? It's sitting on a giant turtle. Well, what is that turtle sitting on? Another giant turtle.
Like, who made God? Well, then who made the one that made God? You could just keep going on with it, right?
Exactly. But so, if you can imagine the 11th dimension is a dimension that is dimensionless. It in the Bible, it's called the void for people who are religious, and it is a void. Another way of looking at it, an analogy would be an electrical ground, whereas a ground wire going into the ground, no matter how much electricity you put into there, are you going to fill up the ground with electricity? Professor Alan Guth, he's the guy who came up with, of course, all these physicists love to support each other, so there's a big problem with the Big Bang, and that is that for our universe to be the way that it is now, it couldn't have just banged out, because stuff would have... Our universe is actually very smooth.
You know how my friend puts it? He says for there to be a big bang, there had to be a big banger, he says.
Right.
And that's how he puts it. I know it sounds weird, but it kind of makes a little sense.
Yeah, we don't know what caused the bang. We don't know how it banged. We don't know why it banged. We don't know if there was anything before it banged. And we don't know what happened right after it banged. Because if the Big Bang Theory is the way it is, then our universe would be all clumped up. In fact, there was another problem with the so-called Big Bang Theory, and that is when there was a supposedly Big Bang, then there was equal amounts of normal matter and equal amounts of antimatter. Now, in Physics 101 classroom textbook, it'll say, well, there was just a little more normal matter, and it won the war and destroyed all the antimatter. So our universe is normal matter. But that wouldn't be true. It would be equal amounts. And if equal amounts of matter and antimatter were formed at the moments after the Big Bang, as they all, the equations show that. The measurements of the background radiation of our universe tells us that there were equal amounts of normal matter and antimatter. So if there were, they would have annihilated each other, and our universe wouldn't exist.
So, I mean, the universe is constantly expanding, they say. So
yes.
If that's the case, then we're moving along with it. Isn't it possible that two universes eventually can cross one another?
Well, there's several things that say you're absolutely right. You're talking about dark matter and dark energy, and there's also something called dark flow. And there's another, well, let me explain that. There are galaxies moving through the universe that are observable. They have names and everything. And there's no reason for them to be moving the way that they're moving. If you look over here, you see this galaxy. Well, it's that way, and it's moving that way because of this other galaxy, and gravity is doing that, and these things are moving away because there is a supernova there. But these dark flows, I think there's 3 of them so far found, is matter moving through the universe that has no reason to be moving the way it's moving. It has no reason to be there. And so some theorists believe that what you're looking at there is matter from a parallel universe moving through our universe. That can be the only answer.
Okay, Chris and Tony, we got to take a break here. Tony, I don't know if that answered your question. Or
Yeah, I'm good. That was good. That was good, yeah.
All right, well, listen, thank you for calling in, but I really got to get off to this break. So
no problem.
All right, thanks a lot, my friend. I appreciate it. Chris, just hang on the line. We're going to take a break. We'll be back.
Staring at their hands.
Yeah, I'm seeing those same reports.
Listen, maybe some of your listeners are kind of skeptical about this parallel universes thing. I just got to let them know that their tax dollars are at work searching for parallel universes. Remember I said that there was a big problem with the Big Bang, which I didn't intend to talk about tonight, but here we are, that at the moment of the Big Bang, or Big Bump, that there was equal parts of matter and antimatter. Well, they don't. So if the equal amounts would have destroyed each other, because when antimatter and matter meet, they annihilate each other, that our universe wouldn't exist. So some astrophysicists think that, well, that antimatter split away from our universe and created a parallel antimatter universe. Now, next month, if there's no leaks in the space shuttle Endeavour, they're blasting off with an instrument. Probably it is so far the most expensive instrument that has ever been taken to the International Space Station. And if your listeners want to look it up, they go to spaceflightnow.com, and that's like the newspaper for NASA, and put in under search STS-134. And they're putting up this $2 billion Oh, by the way, Congress had to vote on it to give an extra space shuttle flight to carry this payload.
Well, they're voting on that, but not bombing Libya. But I won't get into that either. Go ahead.
Congress authorized an extra shuttle flight to deliver this experiment, this astrophysical spectrometer is what it's called. And its purpose is to look for and find an antimatter universe.
And how close do you think how positive are they that they're going to find this? And will they tell us about it if they do?
Well, it's funny because a couple of months ago it was on the NASA site talking about the antimatter universe, and now they're just talking about, it's looking for dark matter. It's completely gone now. And why they took out the whole thing of what it is, I'm reading from their release right here. At the moment of the Big Bang, there must have been equal amounts of matter and antimatter, otherwise we would never come from the vacuum. So you have a positive charged electron, negative charged electrons, blah, blah, blah. You must have antimatter, but the antimatter disappeared, and raises the question, where did it go? So that's what they're doing. They're actually looking to find where this parallel antimatter universe is. It's not science fiction. That's your tax dollars at work.
Oh, I believe it.
Okay. Now, let's move on. We talked about wave function collapse, the observer effect, that you look at something and it goes from being a wave and it turns into a particle when you observe it, when you look at it. In fact, when you're looking at light coming at you, it's coming at you as a wave. It turns into a particle only after it enters your eye, and where your eye converts that particle to an image and you see. So there's this paranormal thing that reality is paranormal. It really is. that what we see, we make it by observing it. But there's something else that is a crazy paranormal thing about reality, and that's called quantum entanglement.
Now, what is that?
It's another phenomenon that exists in our world that is a scientific fact that is not explained, cannot be explained. By definition, it's paranormal. A quantum entanglement is probably the most baffling phenomenon known to science. Albert Einstein called it spooky action at a distance. And here's why. In the physics lab, two identical nuclear particles, A and B, they're generated and sent in opposite directions. An apparatus is used to alter the state of one of those two particles. We'll call it A. At the same instant that we change that state of that particle, the second particle, B, will simultaneously change its state to match that of particle A. And this will happen no matter how far apart A and B are from each other. In theory, the two particles can be on opposite sides of the universe, and the results remain the same. Notice, how does particle B know that the state of particle A has been changed? How does particle B change its state to that of particle A without an apparatus to cause the change? And how does the information that particle A has been changed travel across the universe to particle B faster than the speed of light? In fact, in 0 time. No one can answer that question. Nobody. Now, one theory attempts to explain the question by supposing that at the moment before the Big Bang, all matter was in our universe was all combined together.
Well, it's said that only light travels at the speed of light right now. Isn't that what's believed? That I've heard from scientists that spoke out and said, it's impossible to travel the speed of light.
Yeah, that's why this is a phenomena, and it's the most baffling. And it's done every day in physics labs around the world, where you create two particles and you send one way and one the other way, and you make one of the particles change, the other one changes with it. And they do not know why. And exactly what Einstein called it. It's spooky action at a distance. And now again, want to talk about your tax dollars at work.
Oh, I love talking about that.
If your listeners want to go to the Boston Globe website, there's an article that came out. It was on March 14th. It's called Beyond Radar. And like they say, imagine two photons, basic units of light. You change one, the other one automatically changes no matter how far apart they are. Well, our government is taking that a step further, and they're making a radar that sends out a photon, and they point it at a satellite or a fighter jet, whatever they want to paint on the radar, and that photon sends back information to its brother photon back at headquarters, telling the photon back at headquarters what the photon out there striking the airplane is seeing. It's entanglement radar.
That's some good intelligence right there.
Now, that means, let's extrapolate that a little bit. Okay, all these electrons and protons and neutrons, that's what we're made out of. And somehow, all those particles, if you separate them and change one, its partner will change immediately. Superliminal. That means faster than the speed of light. Now, science comes up with all these things to try to explain how that's possible. How something as paranormal as particles are conveying information from one side of the universe to the other faster than the speed of light. There's some experiments where they can place mirrors and light from stars put into the apparatus, and again, this is paranormal, that these particles seem to know whether you're going to put the mirror in the apparatus or not. But that particle left that star millions of years ago. And it's going to know whether it's too complicated to try to explain the apparatus and how the experiment goes.
So the source of that light has actually died, say, 1 million years ago, but the particles from that light are actually still existing. Well,
true. But beyond that, how does that particle know you're going to be putting a mirror in there?
Intelligence. That's all I can say. It has its own intelligence.
How can a particle on one side of the universe tell its partner that I'm no longer a right-hand spinner, I'm a left-hand spinner? And so that second particle immediately starts spinning left-handed. So, again, this is just one of dozens of quantum physical phenomena that is unexplained. Now, one of these things about how this information is carried across is they invented a particle called the tachyon. You ever heard of tachyons?
No, I haven't.
Oh, you hear it
sounds like a clothing or something.
Well, you hear it in Star Trek and, Star Wars and things. Well, we're sending tachyon pulses through the... Well, these are particles that actually exist outside of time, and so they can travel faster than the speed of time, faster than the speed of light, like warp speed in Star Trek with their...
Oh, yeah.
Yeah, well, they get their propulsion from antimatter, by the way. Now, then there's another thing. It's called, virtual particles. Now, let's say I send an electron from an apparatus to a target. Now, that electron leaves the apparatus. It's traveling at the speed of light, or close to it. But it takes twice as long for it to hit the target. Wait a minute now. It's leaving the apparatus at the speed of light, okay? So it should hit the target in so many millionths of a second from now. But it doesn't. It takes twice as long. You can put sensors all along the path of this electron that you've just fired, And every one of those sensors will tell you, yep, that electron's moving at the speed of light. Yep, moving at the speed of light. But it takes twice as long to get there.
Why is that?
Well, nobody knows. It's paranormal. So what do physicists do? They invent something called a virtual particle. Now, they say, this is their theory, is that there's these particles that come up out of the vacuum, called zero-point energy, by the way, just the energy of the vacuum, and they appear, and they stand in the way of your electron. So the electron has to zigzag around these invisible virtual particles, which, by the way, they've never been seen.
Mm-hmm.
But they know that there must be something that's holding back the electron. Why is it taking twice as long to get where it's going, but it's still traveling at the speed of light? So they said, okay, well, it's having to travel a greater distance. It's not going 10 feet or whatever, however long your apparatus is. Could be 1,000,000 miles long. It doesn't matter. So these virtual particles just pop up out of nowhere, and they're standing in the way of the electron. So the electron is zigzagging. So that's their answer to virtual particles.
And you say antimatter is actually how they would run those propulsion systems. Now, do you think that, say, secret space program, military have already mastered this and that they're able to actually build craft now that can move at the speed of light?
I can't speculate on that.
No.
But I know we can make antimatter. We've been making antimatter since the 50s.
So if we can make the antimatter, couldn't we? I mean, is it scientifically possible to create a craft that would go speed of light? Or maybe take the human being and, like they do on Star Trek, transform them, transport them in the particles.
Well, still, if you transport particles, you're still going to have to get around these virtual particles that are in your way, so it's going to take longer than the speed of light to get there. Traveling at the speed of light, you got a whole lot of problems, and that's why in Star Trek they put a warp bubble around the Enterprise. They change the space so that it is warped, it's dilated. And if you can do that, it's possible to travel faster than the speed of light, but it would take so much energy, it's just incredible. Yes, antimatter is, when it meets normal matter, is the most powerful energy in the universe. There's nothing, you're not going to get any more energy out of anything than the interaction of normal matter with antimatter. Problem with going at the speed of light, if you're just normally going at the speed of light, is when you say speed of light, you're saying the speed. How long does it take to go from here to there? So, it's 50 miles an hour.
I think of like turning on a flashlight, in a dark room, turn on the flashlight and see, that light hits the wall. As soon as I hit that switch, I mean, it's that fast.
Yeah, it's several million feet a second.
Mm-hmm.
In 1 minute, your flashlight will go around the Earth 7 times.
Wow.
But 186,000 miles a second. And the Earth is 25,000 miles around at the equator, so you do the math. The problem with this is that as you go faster and faster, your mass increases. And so what today's scientists will say is that the greater your mass, the more energy it's going to take to push you. And so your mass becomes so great that it would take all the energy of the universe to push you up to the speed of light.
Okay, Chris, hold that thought right there. We've got to take our short break here. This will be in a moment. Unfortunately, it's hard for me to really keep up with the chat because when somebody says something, that chat room kind of goes crazy there. And I just can't keep up with it and do what I'm doing here. So yeah, Nova's going to try to get a few of those questions in just a few minutes. The website is Late Night in the Midlands at, LateNightInTheMidlands.com, and the email address is LateNightInTheMidlands@yahoo.com. I'm trying to keep my eye on her, making sure Nova gets her mic ready and so on. So that's my excuse, and I'm sticking with it. But let's get back on with Chris here. All right, Chris, we are back, my friend.
Michael, listen. There are parallel universes, and you are in those parallel universes. So there is a Michael Vera that can do all these things at once.
Oh, I'd like to meet him. I really would.
Let me straighten one thing out. I didn't get to finish talking about it. It was the virtual particles. Science says that these things come from the vacuum. Those of us who are in the parallel universe side of the coin say that these virtual particles are actually coming from parallel universes and interfering with our universe. Mm-hmm. Okay, we're through with that. Now, you were asking me about traveling at the speed of light. The faster you go, the greater your mass, which means you become heavier. Mm-hmm. Well, the heavier you are, the greater your mass is, the slower time passes for you. So, as you reach the speed of light, your clock stops.
So basically, you wouldn't age if you stood at the speed of light, or at least not anytime soon.
Right. That goes back to Einstein's parody about the twins, the twin astronauts. I heard about that when I was in 6th grade, where you've got two astronauts. Two twins. One is an astronaut, and he goes off into outer space in a spaceship traveling at the speed of light. His twin brother stays here on Earth. When the astronaut brother comes back, he hasn't aged, but his twin brother is 40 years older because the guy traveling at the speed of light, his clock stopped. So he didn't age. Now, this is not science fiction. This is a fact. It was proved. It's Einstein's theory of relativity. It was proved in 1957 in Harvard. Something called, what was it called? The Robert Pound and Glenn Rebka experiment, the Pound-Rebka experiment. And, 1957, at Harvard. And what they did was they shot some gamma rays on the ground floor of the laboratory that they were in up to the roof, 3 stories up. And they had a clock down on the ground floor and went up on the roof. And it took longer for the beam to reach the roof than it should have. Mm-hmm. By timing it. Something called the Doppler effect, or the red shift, is what showed up. So people ask, is there such a thing as time travel? I say, yeah, you're time traveling right now. Excuse me? Yes. Your feet are going slower than the top of your head. And it's true. The closer you are to something of great mass, like the planet Earth, the slower time goes. The further away you get from something of great mass, something of gravitational pull, the faster time is. If you're up in a 10-story building and you're looking down at the people on the street, they're actually in the past. Now, the difference is 0.0000 with 35 zeros of a second difference, so you don't see any difference, but the difference is still measurable. And it was proven again in the 1970s with some atomic clocks put in airplanes going different directions around the Earth. So this time dilation is a fact. If you use a GPS in your car, the GPS satellites, the clocks on those satellites have to compensate for the fact that they're so many miles away from Earth. So their clocks are moving faster. But at the same time, they're moving at 17,000 miles an hour, so their clocks are going slower because they're going faster, like I told you about with the twins. So you have to adjust those clocks to compensate for going faster because they're further away from the Earth and going slower because they're traveling so fast.
Okay, now some people feel like time is speeding up on this planet. Is there actually a way that can happen?
Well, we're moving at over 100,000 miles an hour.
Mm-hmm.
So our clocks are what you call relative to the observer, another Einstein thing. If we were moving faster or slower, we wouldn't know it.
Right.
Because everything else is moving at our speed. So, no. Now, there is a phenomenon, and I get into it in my book.
We're talking paranormal again.
Yeah. And this is another thing that science will argue with you about. Have you ever been in an accident or almost in an accident, and it seems like time is going real slow?
Yeah, absolutely.
You know, not everybody feels that.
It's like when I was a kid, my father used to come at me and kick my butt for doing something bad. During that butt whooping, boy, time seemed to just stop. I know what you mean.
Yeah, I remember when I was a kid being in a bicycle crash, and it was like moving like,
exactly.
You know, and I'm watching the handlebars as they pass under me as I'm flying through the air, and I'm seeing the road coming up at me, and it just seems like time has slowed down. Well, some scientists will say, oh, well, that's just chemical reactions, and, you know, your brain, it's a survival thing. But others said, well, wait, let's test that. And they did. One professor took an instrument that was on the wrist of his volunteer students that had numbers zipping across it. And he would adjust those random numbers so that when the student looked at these numbers on this apparatus that's on their wrist, the numbers are moving so fast they can't read them. Okay, now let's take that student up into a crane, 150 feet off the ground. We'll put a net underneath them, and we'll drop them and see what happens while they're watching these numbers that they cannot read. Mm-hmm. Moving across this apparatus on their wrist. So they take them up, pull the cord, and drop them. When they hit the net, the professor comes over and says, did you see the numbers? And they all said, oh, my God, I did. I could read the numbers. They were 3, 4, 7. The next guy, it was 7, 8, 2. How is that possible? That's paranormal. Where here are these numbers while I'm standing here on the ground. I can't read them. They're just zipping across my little screen so fast, I can't tell what they are. Mm-hmm. Now I'm dropping through space, and my body thinks I'm going to die when I hit the ground. It doesn't know that there's a net underneath me. And now I can read the numbers. So that professor concluded that, yes, time is slowing down for that person, not because they're falling. His thesis stated that, well, all these parallel universes are interconnected.
So two different realities.
Right. Mm-hmm. It's Schrodinger's cat. You ever heard of Schrodinger's cat?
No, I haven't.
This physicist at the turn of the century had a mind experiment, and he said, well, if we took a cat and we put it into a box and we put an isotope in there that would degrade at any time, we don't know when it's going to degrade, and it's going to poison and kill the cat. So there you have this cat in the box, and the cat is either dead or alive, and you don't know until you open the box to know if that cat is dead or alive. Well, that's really the start of the parallel universe idea, 1905, 1906, where they were saying, well, there's actually two potential realities there. And then along came this fellow Heisenberg with the Heisenberg principle, where there's so many different outcomes that you don't know how many, the cat could be half dead, could be half alive. It could have had a litter of kittens. It could have became a kitten itself. It's just all these different outcomes are unknown. And that's where the idea of parallel universes first began, because we don't know. There's all these different choices, and these choices are not made until we make them.
You know, you kind of answered one of Nova's question, was that, you know, these parallel universes, does that mean that there's more than one of us, that, you know, that we're in all those dimensions?
Well, I don't like using the word dimension. That doesn't tell us anything. That's a spatial vector. I mean, you go ahead and use it, but it doesn't tell you anything.
All right, so these parallel universes. All right, so each one, we're involved in them all?
Well, again, there's different kinds of universes. There's multiple universes. Those are the bubbles I was talking about.
Right.
Those don't have anything to do with us. Parallel universes are ones that are parallel with us. They're right beside us.
Well, I guess what I'm wondering is when our universe kind of parallels with, say, the ghost universe, is that how we see ghosts and stuff? Is that what's going on? I mean, two universes going parallel?
That's a theory. Certainly is. That's why I'm on the paranormalexperiences.net. I'm questioning ghost hunters. I'm trying to find out how EVPs can work. How can a ghost move air molecules? On and on and on. But no, that is one of my theories, and certainly others, that that's what we're experiencing, that we're somehow, maybe the clairvoyant types are running across areas where there's an overlap of parallel universes, and some of these things we're seeing are parallel universes that are in the past of us. And then there's parallel universes that are in the future of us. So sometimes we can be actually seeing things in the future. We're way off from the anthropic principle and the fundamental constants and the things that I was going to talk about tonight. But this brings into UFOs. There's how in the world is there going to be a spaceship that's going to go 100,000 light years across the universe? That's going to take 100,000 years to get here, traveling at the speed of light.
I think they know a secret.
Yeah, the secret is they're not coming from someplace out in the universe. They're from parallel universes. These parallel universes, it's a fact that subatomic particles, atoms, and even molecules can go to and from parallel universes. That's a fact. That's not science fiction. Look it up. Google it.
See, I also believe that some might be coming from nearby, you know, because obviously, you know, we've never been to all these planets and these moons that are near us, so we really don't know what's going on up there. So, I mean, I love your theory. I believe in that. I think that that's definitely something that's going on and possible, but I also think that we're being visited from other planets.
Well, sure. I'm not going to exclude that, but look at it this way. We know for a fact that matter moves to and from parallel universes. We don't know for a fact that aliens or anything else is coming from somewhere else to here.
No, I haven't hugged one yet. So
I'm saying it's easier to move from one parallel universe to another parallel universe, because they're right here, than it is to travel across the cosmos. And we have evidence, we have factual evidence that it happens all the time. It's happening with you and me right now. And some physicists think that you and I, everybody, is kind of, sometimes we're in the next parallel universe in the future, and sometimes we're in the parallel universe that's closest to us a little bit in the past. But it's so exactly the same as this one that we don't see the difference. Just like when you're up in a 10-story building and you're looking down at the people on the street, they're in the past, but it's so close, time-wise, that we don't see a difference. So I believe, and a lot of others, that it's much easier to travel from one parallel universe to another than it is to cross the cosmos, and we actually go in and out of parallel universes all the time. I'm driving down the street, and I go through the red light, I get hit by a car, I'm killed. But the parallel universe guy who's 2 seconds in the future from me, he went through the intersection, didn't get hit. The guy who was a split second in front of me, he got hit and he's in a wheelchair for the rest of his life.
Mm-hmm.
The other guy who didn't leave 5 minutes earlier, he stopped at the light. So these are all these different things that can happen. I'm trying to use words that anybody can understand, that instead of the...
Oh, I understand completely, and I'm late for so many things. I wonder if I was on time, how many times I would have been there just in time to be in one of those not so good parallel universes.
Well, it's been proposed to me and others that you've probably been killed many, many times. You've probably died many, many times.
I wouldn't doubt it. It's my luck.
But you don't know it. That, there's, again, another theory I talk about in the book where people call it souls, but they're not really souls. They're parallel realities of our individual, or individualism. And that we can, since energy can never be destroyed, it just moves to a different place. In our theories is that this other place is parallel universes, that you don't actually die, you move into the next parallel universe where you weren't killed.
I can live with that now. I can live with that.
So there's hope after all, that there is life after death, and a religious person will say, well, heaven is a parallel universe.
It's quite possible. And, in reality, I think it would be, wouldn't it? I mean, really, it very well could be a parallel universe. But I have a couple questions that I want to throw at you from the chat, and you can give me the quick answers on them, and
all
so
right.
I can be able to give you a few minutes to go ahead and get out whatever else you want to get out here. One is, what is the SETI researching? Is that what you're explaining? Has that got something to do with it, like with SETI?
No, SETI is the search for extraterrestrial intelligence. And it's radio astronomy, trying to pick up signals in our universe from other galaxies.
Okay.
Trying to pick up radio signals from other galaxies here in our universe, not other universes.
Okay, so that can't by chance pick up some kind of signals from, say, a parallel universe.
Not that we know
of, right. Okay, now the other question was, we were talking about the flashlight earlier. Now, when you turn that light off, where does that light go? When you turn it off, it's gone. Where did it go? It was there, and now it's gone. Is it still traveling somewhere, or is it gone?
Well, in our atmosphere, the photons hit particles in our atmosphere, and so it decays.
Okay.
Now, in a vacuum, the light will keep going on forever as long as there's no gases or anything solid to absorb the light.
Okay, Chris, we've got about 2.5 minutes here. I want you to be able to go ahead and give out websites, where people can get your book when it's ready, and all that good stuff. So go right ahead.
Okie dokie.
Mm-hmm.
You can, when my book's out, you can go to Chris, C-H-R-I-S, Schweitzer, S-C-H-W-E-I-T-Z-E-R, books.com, and we'll get a copy right out to you. Again, don't expect a novel or a sweet little story. It's very heavy science, and most people roll their eyes or just put it down and say, I don't know what the hell this guy's talking about. And you can always read my blogs on paranormalexperiences.net.
Okay. All right. Well, I got to say, in the beginning, I was a little, stunned with all the science to it. But as we got through it here tonight, I have a much better understanding of it. This has actually been very, very interesting 2 hours. And, Chris, I wouldn't mind getting you back in the future, seriously, and maybe get into this a little deeper. For sure. This is just very interesting. We're talking about parallel universes. And really, figuring that out could actually figure out a lot of things that man has questioned for a long time. So,
I think so.
Oh, absolutely. Well, listen, thank you so much for being a guest, and thanks for being involved at Late Night in the Midlands. I absolutely appreciate it, and keep up the good work.
Thank you.
All right. Thank you, Chris.
Bye-bye.
Bye-bye. All right. Chris Switzer.
What I'm talking about now, this is nothing new. It's not something I made up, and that's the way nature is. And it can be demonstrated. And before we're through tonight, we can. I'll let your listeners see for themselves what I'm talking about with just their bare hands. Kind of a parlor trick I like to show.
Okay, that's fine. Now, tell me about paradoxes and quantum physics and what they actually have to do with the paranormal.
Okay, well, like I was saying about the fact that matter is a wave and it's a particle. Now, matter is in this wave state that I'm talking about when it's undisturbed. It's a wave of energy, and it typically stays that way until it interacts with another wave. When a wave interacts with another wave of greater or lesser energy, it collapses that wave, and that wave becomes an actual solid particle. And that's what is called the wave function collapse.
Now, what about like dark matter? What is all that now? Is that different from what we're talking about, or?
Yeah, that's something different.
Okay.
What I'm talking about right now is just the basic material that makes matter. That is everything that is solid in our universe.
Okay.
But everything in our universe is not solid. It's every little subatomic particle and all the things that atoms are made out of, neutrons and protons. They are not solid particles until they interact. They're waves until they interact with another wave. Now here comes the paranormal part.
Okay.
Now, stay with me for a second. I know it's confusing.
I'm doing my best.
Okay, this wave function collapse is also called the observer effect. It only sounds complicated. But the wave also collapses and turns into a particle, like I was saying, when we observe the wave. I'll repeat that. The wave turns into a particle when we observe the wave. In other words, the wave functions, that is, it behaves like a wave until it is either observed or a measurement is taken. Then the wave collapses and it functions or behaves as a particle. How is that possible? No one, not Albert Einstein, Stephen Hawking, or any other physicist, knows how or why the simple act of observation can affect the nature of reality.
Has this been documented?
Oh, absolutely. Like I said, it's over 100 years old. Mm-hmm. And I'll show you how you can see it yourself with your own bare hands in a moment. Okay. Now, there's a lot of theories, but none has ever shown any promise of explaining wave function collapse by observation. Wave function collapse is more than paranormal. It's supernatural. It's beyond explanation. Now, how is it that if you look at something, it changes? You don't touch it. All you do is observe it. Now, there's something called the slit screen or the double split or the double slit experiment. Now, in the double slit experiment, like I said, it's been seen more than 100 years ago. In a physics lab, a barrier is set up with two closely spaced parallel slits cut in it. Each slit can be opened or closed independently. Now, you can do this with a razor blade and a piece of cardboard. Mm-hmm. You don't have to go into a laboratory, just a thin piece of card, a playing card. They put two razor slits real close together, side by side, half-inch long or so, and in a darkened room, put a flashlight in front of those two slits on the card and shine it onto the floor or onto your desktop. And what you'll see is not two slits of light. You'll see a series of bands.
Right. Mm-hmm.
And these bands, there can be any number of them. In fact, they can, at times, under laboratory conditions, number infinitely. But, again, in the lab, you put up this barrier with the two slits. Now, each one of these slits can be opened or closed independently. Now, that barrier is placed in front of a screen like a movie theater screen.
Right.
Now, with an apparatus much like a movie projector, you can project a stream of subatomic particles, electrons, atoms, or photons towards the slits. The intensity of the stream of the particles is set to a point where only one particle passes through the slit at any one time. Thus, each particle can encounter the slit which it passes through, and it registers on the screen. Or the particle can hit the barrier and is absorbed. Now, even if the stream is perfectly aimed, no one can predict just where an individual particle will land. But every time a particle manages to pass through the slits in the barrier, it leaves a tiny spot on the screen. So you would think each particle must pass through one or the other slit in order to reach the screen.
Mm-hmm.
They don't.
What do they do then?
They interfere with themselves. And that creates this pattern, the pattern of the series of separated bands, the sequence.
And my guest, Chris Schweitzer, and I hope I'm saying your name right, Chris.
That's close enough. It's actually Schweitzer.
Okay, Schweitzer. Sorry about that. How are you tonight?
I'm great. It's really a pleasure to be on late night in the Midlands.
Well, it's just as much a pleasure to have you here tonight, so I have a feeling I'll be learning something.
I hope so.
All right. So I guess why don't we start out? Tell me a little bit about yourself and then a little bit about this book.
Well, I'm a paranormal researcher,
mm-hmm.
and I'm also a quantum physics researcher. And when you put those two together, you come up with some things that are awful close together. They call me the reality is paranormal guy.
Right.
What I do is I show the skeptics and the critics who dismiss paranormal experiences that the physical world is just as bizarre and just as inexplicable as that which is found in the realm of paranormal.
Okay, so what do you mean by that?
Well, I challenge the critics and skeptics of paranormal experiences with examples of how nature acts in bewildering and mysterious ways that no one can explain. I do that by explaining the simple fact that everything, all forms of matter, what you and I, all of us are made out of, or composed of, in fact, our whole universe, that the very laws of nature are by definition paranormal. So what is the definition of paranormal? It's something that is impossible to explain scientifically, or something that cannot be understood in terms of scientific knowledge.
Mm-hmm.
Now, with the numerous unexplained paradoxes found in quantum physics and cosmology, they fall under that definition. Nature does things that, by all intents and purposes, are impossible to understand by our understanding. I can give you some examples.
Yes, please do.
In quantum physics, there's something called the wave function collapse. It's also called the observer effect. And it's a demonstration of the duality that is the dual state of matter. All matter on the subatomic particle level exists as both a particle and a wave. I'll get into that later, but right now we're just get a little groundwork going here.
Yeah, a little understanding.
Right. So like I said, it's scientifically proven fact that all atomic matter exists as both a wave and a particle. To visualize what I'm describing, you have to eliminate that picture we were all taught in school where we were told that an atom is a nucleus with electrons orbiting around it like planets orbiting the sun.
Mm-hmm.
But the truth is that electrons are, in actuality, they're a wave just like in a pond. It's actually a wave of energy. It's not a particle. And like all waves, the electron wave has a crest and a trough. Just like when you're surfing a wave, you're up on the crest and you surf down into the trough. Now the energy of the wave, the energy that is in the electron dictates the height of that wave or the crest of the wave as it races around the nucleus. So if you can imagine a wave with a peak and a trough, and that's what's moving around the nucleus. It's not a solid particle.
Okay.
Now, it was discovered over 100 years ago